Thank you. Okay. So what one is asking you to do is, we've already seen this before. It wants you to count the carbons and count the hydrogens. So you've seen two big questions like this where you're given a very scary looking molecule and you have to count the carbons and hydrogens. Does anyone have trouble doing that? Okay, that will be on the exam. One question like this will most likely be on the exam because we've seen it pop up on every practical exam so far. So it will be a question like this. So if you can count that, good. If you can't, come talk to me. We have some problems with take care of. Okay. Number 2 is drawing isomers. So that basically just means we're going to draw the same molecule, but a little bit different each time. And I have to do this structure. What does that structure look like? Yep, every college student's favorite molecule, alcohol. Alcohols can be on primary carbons, secondary carbons, and tertiary carbons. Okay, you get any of the answers? Yeah, I can do that. Should I stop? See this? Don't see me. Okay. So let's count the hydrogens. Okay. So here, 1, 2. So it's 1 carbon. Oh, sorry, 1 hydrogen, 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 hydrogen. 2 hydrogen, 1 hydrogen, and 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is 10E. Sorry, is 1E. Let's look it up real quick. And 1 is E. There you go. That makes sense? Whoever the person that asked the question. You can speak or you can write. Okay, cool. Nice, nice, nice. Nope, don't stop sharing. Did I stop sharing? Why would I do that? Okay, continue onwards. Okay, so we need to do alcohol now. All right, and it can be on a primary, secondary, tertiary. If you have no idea what that means, watch yesterday's video. But basically, it can be on a carbon that is by itself at the end. It can be on a carbon between 2 carbons, or it can be a carbon that is surrounded by 3 other carbons. So it can basically be anywhere. So we're gonna get a lot of possibilities. All right. So let's do the simple one. Okay, 4 carbons, right? I'm not going to draw hydrogens because it takes too long, but alcohol will be right there on the very first carbon. That's allowed, right? Okay. Then I will put it on the second carbon. Right? Is there more we can do? Like, yes, there is. I could make a branch and put the alcohol on the middle carbon again, right? I could then make the exact same branch and then put the alcohol on that carbon, right? You see that? So the answer is 4. The reason why I can't put this alcohol group in any of the other carbons, right? Is because if I do, it's the same molecule. It's gonna, if you just turn the molecule, it's exactly the same thing. There's mirror images of each other. Does that make sense? Or no? Yes. Can I do what? I can draw those. Do you want to draw those out for you?
Yeah, just confused.
Okay. I don't like, okay. I don't do line dot very often because a lot of students don't like it, but if you want me to do it, sure. 1, 2, 3, 4. All right. Here's your OH. 1, 2, 3, 4. Here's your OH. All right. You kind of basically make a cross, OH, and then you make another cross. This time OH is down here. There's your 4 structures you can do. That makes sense or no?
Why can't you put OH on the end of the second one?
Why can't I put OH on the end of the second one? Like this right here? On the end? Because it's already on the end on this one. 1, 2. Carbon branch, what carbon branch? This right here? It's not a branch. 1, 2, 3, 4. There's 4 carbons there, right? I attached the second one. Okay.
So if you erase that OH on the top,
Okay.
you put OH on the far right.
I erased the OH. It wasn't a branch. It was connecting it.
I know, but if you had that carbon going up, isn't that still a different structure?
A carbon going up. What carbon going up?
Just a line, like how you had with the OH.
If I like that.
And then had the OH on one of those sides. On the end.
You mean if I erase that carbon right there?
No, you could still keep that.
Okay. 1, 2, 3, 4.
Still draw that line up and write an OH.
Okay, sure.
Why wouldn't that work?
Because I already drew that. I just did it differently.
Why?
When I did this cross symbol I did, right? Technically that is the same thing as that. I just did not do it in a totally line angle. I did a cross instead. So the answer is 4. Okay. Benzene penicillin G is used to treat diseases such as strep, staph, diphtheria, meningitis, gonorrhea, and syphilis. Why they give that GCU a lot. That's why he brings it up, because it's one of the biggest things given out by the school to students. The freshman dorms, guys.
I was like, oh yeah, structure, okay.
Yeah, lopes up. We beat ASU somehow in this category, which is scary.
Hey, we're private and Christian.
Yeah, that's good. Okay. So we have to choose which of the following statements are false, right? So I'm gonna put check marks in your correct ones, correct? Okay. The benzene has 1 aromatic ring. True or false?
Sure.
That aromatic ring is right there. Okay. It has 1 heterocyclic ring.
Sure.
That's that guy right there. Hetero means different. Cyclic means ring.
It has to.
Yes, it does have 2. Has heterocyclic rings, so it's good. Okay. Has 2 amides. Yes or no? True. 1, 2. You don't see those. That is a nitrogen bonded to a carbon, which bonded to a double bond, oxygen. Okay. The structure shown has a carboxylic acid group coming forward out of the plane. False. That is the false statement. Right? It's going backwards, going into the page. And lastly, this statement right here is true. So one of the statements is false. There might be 2. You're right. In a second. I might have jumped the gun. Yep, you're right. There is wrong. That is true. Thanks for catching that. There is more than 10. There's like 14. So wrong. So the answer is B. Okay. My bad. Okay. Hey, look, structure 4 is existing. So now we've done this question multiple times, different ways, right? Hint, hint, wink, wink. This will pop up on your guys' test. You have to draw isomers given the structure you have to form. Make sense? It's a good way to test multiple concepts at once. So what is an ether? There you go. So it has to form like that, right? Okay, and I'm playing with 4 carbons. So let's draw the easy one first. Carbon, oxygen, carbon, carbon, carbon. right? And then we can move it a little bit to the middle. And that's it. Those are your two options. The reason being is because it needs between two carbons. And since you only have 4 carbons total, you can't really make anything else from it. Okay. So you have 2 isomers. But, oh, never mind, I messed up. There is one more. One, two, three. Ooh, what is the third one? There are 3. You can branch, yeah, you're right. I forgot the branch. I always forget the branch ones. Dot. And then make a branch right there. Okay.
I think there's 4. Because you can do the box one.
Nope, we can't do a box one.
You can't do a box one?
Box is how many points? Box is how many points? How many corners does the box have? So there's 4, you have to have 4 carbons to make a box. Can I do 5 carbons?
You do a pentagon.
No, you can't, no. So it's gonna, the answer sheet says it's B, so we're gonna say it's B. The reason why is basically it's the same thing. Drawing cyclic shapes won't work too much.
So there's 3 for sure.
There's 3 for sure.
Oh. Wait, would it not be like a circular kind of shape, because then it would be an epoxide?
Yep, exactly.
It would be an epoxide.
An epoxide is an ether that is in a cyclic formation. So for example, that's an epoxide. See how it's an ether, but it's in a, it's a formation? That's an epoxide.
You know?
Okay, that makes sense.
That's an epoxide. Okay, 5. Hey, this question pops up multiple times. What's that mean?
It's gonna be on the exam.
Yes, you have to know your functional groups. If you don't know your functional groups right now, go to Google, type in functional groups. There's probably tons of charts. Make flashcards. Start studying now because you have until tomorrow, pretty much. Okay. What's this one?
It's a alcohol.
I eliminated all the answers except 2. See how easy that was?
Wow.
These are give me problems pretty much. Okay. Amine or amide? It's an amine. Amide has to have a double bond. So the answer is A. Alcohol, amine, amide. Okay. Zoomies, you got all that so far?
Yeah, we're good.
Okay. Is Emily there with you, Mackenzie?
Yes, she is.
Yeah, I am.
Are you charging your laptop? iPad?
Yes, I am.
Okay.
Can you tell me if Athena is on there?
Athena's on there.
Okay.
Why?
I just wanted her to send me the thing.
The thing?
She's like, you just have to memorize something with the functional groups, and
Athena, send Jocelyn the thing.
I don't have any contact. I'll just join the thing.
Okay, Athena?
What did she wants me to send her? What?
The thing. I don't know what it, she won't give me a name. She just calls it the
It
thing.
was like the functional group, number thing.
The functional group number thingy, bobber.
She says,
Oh yeah. Oh, okay. I know what she's talking about. I don't know how to send that to her. I don't have her number or anything.
Well, she just joined the call. She put a number in the chat. Hi, that's a,
How do I put it in the chat?
she's gonna put it in the chat.
No, how?
Okay, she just joined the call.
Well, am I supposed to take a picture? Like, I don't.
She's texting her number and then,
Oh, okay. I got you. I got you. Okay.
Okay. I'm not gonna look that up because it'd be kind of weird because apparently people outside of GC look at my videos now too, which is scary
Really?
because they're going way higher in views, which is not good.
Might drop out and become a teacher.
No.
yeah, that could be.
Because apparently one of my students didn't know I made YouTubes and she typed in chemistry help with math and my face was like one of the first popped up. which is,
You make like t-shirts.
they'll make t-shirts.
OGs know, yeah.
Which reason best explains this? So K, remember, K is equal to products over reactants, good. And I want a more stable product. Okay. This guy right here, base or acid, why? That is one way of thinking about it. We don't do Bronsted-Lowry unless we tell you to Bronsted-Lowry. It is, luckily, but assume it's Lewis instead. Unless the question specifically says use Bronsted-Lowry definitions, you have to use Lewis.
So it's like donating. So
Yes, it's negative, right? Which means it's electrophile or nucleophile? No, neutrophile. Okay, what does electrophile mean? What's electro mean? Loves electrons. If you already have an electron, can you love that electron?
No.
No. It's positive things that are electrophiles. Negative things are nucleophiles. They get rid of the electrons. So they don't care for them.
Okay.
So if that's the base, that's the acid, right? What's that make this guy right here? A conjugate base, conjugate acid. And I'm looking at the conjugate base, right? Cat. So which of the following is true? Which one is it stronger or is it weaker?
Strong.
How do you know it's weaker?
because it's going to the product side, so that means that the acid is stronger.
Good. Yep. So the answer is, why you're not working, don't do this on me. Answer is A.
Sorry.
A weaker base because it won't go, it's not equilibrium, right? So it can't go backwards, right?
So which one's weaker?
The base, the conjugate base is a weaker base.
Conjugate base is weaker than the normal base.
Yes,
Because it can't go backwards.
it can't go backwards. And the reason why it's weaker is because of resonance structure, right? Because resonance structure does what? It stabilizes things, right? The more resonance you have, right? The stronger the acid, the weaker the base. Correct? Make sense? With acid and bases, if you can either just focus on one or the other, and if you know all the characteristics that make one strong, i.e. like all the acids, then you know exactly what makes bases strong as well. It's the exact opposite. We go with that one? Zoomies? Okay, I'm gonna go to the next one then. Hello. Okay. So, which one's the electrophile?
The second one.
Don't care about 3 and 4.
Second.
Why?
Because it's not the neutral.
This is negative, right? That's the neutrophile, which means 2 has to be the electrophile. So 7 is B. That's pretty simple, right? You have to know electrophile and nucleophile by definitions. If you don't, come see me, come talk to me for your quiz. We'll hopefully go over it real quickly. But just know 95% of the time, the negative number is a nucleophile and it is the base. 95% of the time, the positive one is the electrophile and it is the acid.
Would it be approximately 100% of the time in this class?
No, because we'll change it based on what it's being dissolved in or the reagent we're using. You guys have not gone into reagents yet, so most of the time I would say yes for this exam, right? But it is Grubbs. He could pull out the one time it's not, which I don't know exactly all the times it's not, so I can't really give you a good definition, but I can just tell you with most certainty that's how the best way of approaching it. Okay, 1, what structure is that? What's functional group? There is an H coming off of it. Be very careful of that. It's an aldehyde. It's not a ketone, it's an aldehyde. Pretty similar, yeah. What's this guy right here? Nitrite, nitrile. What do you guys think? Nitrile, yep, because there's a T in it, right? The triple bond. And what's this guy right here? That is a ketone. So aldehyde, nitrile. So it would be, it is E.
Isn't it ketone? Am I wrong?
Aldehyde is, yes, the issue is that there's a hydrogen coming off of it, making the hydrogen very acidic.
Okay.
Because it's next to a double bonded O. Because due to resonance structures, it could be kicked off. Okay, Zoomies, how we doing?
We're
Good.
Cool. If you have questions, just talk and yell at me and I will stop. Okay. No, headphones. There's my earbud. Okay. 9. How many arrows? Well, let's do it. You see, we keep drawing arrows. Arrows are very important. So first things first, I got this structure. I'm making I'm making these two structures. And then I'm gonna have to use this guy as part of my thing. So if you notice, I'm not adding together, correct? Key function. They're not being added. That's important. What goes on between these two structures? What's the difference between these two structures I just circled? Okay,
And hydrogen.
so it's still what?
And hydrogen.
Still the hydrogen, right? So we gotta make sure, we have to make the hydrogen move, right? Here's how we're gonna do that. I got this guy. Bromine is an example of what? A
Hydrogen.
halogen, which are good leaving groups. They leave. They always leave. Because they just want one more electron, right? So if they leave and break that bond to the carbon, they can take that oxygen, that electron, they will be negative, right? But they will have a full valence shell and they'll be happy. Right? So most halogens are leaving groups because they want a full octet and they will not usually react unless circumstances say so. That's one arrow, right? When bromine leaves, it takes the oxygen. What's that carbon left with then? Less or more electrons? It lost its electrons to bromine. Does it have less than it started with or more than it started with? Less. So is it positive or negative? So it's positive. So let's do that in different colors so you don't confuse the arrow colors up. Let's do it in hot pink. That carbon right there is now positive, right? Because bromine left, taking the electrons with it. Has one less bond. So it has less electrons, less making it positive, right? Okay, how do I get rid of that positivity? What can I do?
Break the hydrogen.
I could break the hydrogen. That's true, I could. And that's exactly what you do. You break the hydrogen. Hydrogen breaks, right? Bonds go there. That's why this carbon has a lone pair right there. Good job. Now I have this free radical hydrogen going around, right? What do I do with it? The lone pairs here. Attack that. So far I have 3 arrows, right? What's going on?
I see that I can't see what's going on. Air going to the bromine and then.
Let me zoom in real quick to make it easier.
Sorry, was it the bond? You're thinking of?
Oh, hi, Nicole. Yeah. Bromine leaves,
Okay.
right?
Uh-huh.
That's good. Which makes this guy positive, right?
Okay.
That bond will break, right? Making that chlorine, making that carbon normal now, right?
And that counts as a step.
It counts as a step, yep. Because now we have hydrogen here, kind of kicking it as a proton. And we have lone pairs over here that will snatch that out, right? Do you see the 3 arrows so far?
Yes.
Okay, there's your 3 arrows. Okay, we got 3 arrows. I'm going to, now we have this molecule, all right? Okay. What's the difference between that molecule and that molecule? The 2 I underlined. The one that looks like a lung and the one that does not look like a lung anymore. Looks like a barbell.
The chlorine is not two. Oh, it's a carbon.
That's a carbon.
That's-
So carbon and.
Okay. Where does that come from? If you notice something, I don't lose anything, right? So where do I get that triple bond from? Well, apparently carbon. Which you form a triple bond there. One, two, three, four. Hello. 1, 2, 3, 4. Where's your fifth one? I only see 4.
oh, the
He says
guy
5.
told me that you would move the lone pair down and then that double bond would go, or one of the bonds would go, or the that double bond with the one right there would move up to the carbon, so then that's what we flattened out. That makes sense.
You're talking about messing with the benzene rings?
No, the carbon, the double bond to the carbon,
Mm-hmm.
this one right here.
Okay.
That one would, those electrons would move up to the other carbon and then form a bond.
You talking about those electrons right there, or these electrons? Come draw it for me.
Oh, the carbon right below that, the one connecting that double bond.
You said you would, can
Yeah.
I, that these,
Uh-huh.
oh gosh, this is weird.
Just
How
draw.
do you even know?
Because you're leaning on it with your hand.
Okay, so these would form right there, and
Uh-huh.
then this would form right here. You would take that away to make that triple bond and bring the carbon down. So then that carbon's right here. Does
1,
that make
2,
sense?
Well, because I think if you move the lone pair down, that's 16
1,
oxide,
2,
isn't it?
3.
Yeah, so that's why you're gonna move that.
Yeah, 5 bonds.
1, 2, 3. 1, 2, 3.
That's what the guy.
That's very annoying. I don't know why he would make you do that, but yes, that does true. You would technically break that bond. And then you would not do that because you're playing with benzene and he doesn't like you playing with benzene and silicon too. Because benzene is stable structure and it does not like losing things. But yeah, I could see that. The answer is 5, but I don't like it. So we're gonna skip it. Okay, 10. So do you guys like acids or bases more? Which ways you like better more? Acids? So what makes a strong acid? What makes an acid stronger? Resonance. And well, first off, it's the atom with the charge, right? And then it's resonance, and then it's hybridization, right?
And size.
Well, that's the atom.
What about the?
That's polarity. That's about size. That's dipole, which has to do with electronegativity, which is the atom itself. You see how dipole size and all that can be all defined by the atom itself. That's why that's the most important one, right? Then it's resonance, then it's SP, hybridization. Good. So which one has resonance? 2. That should be your strongest acid, right? Does that make sense? That should be a strong acid. If that's a strong acid, what base is it? It's a weak base. So 2 is going to be your weakest base because it's the strongest acid up there. Okay. Which one is bigger, S or O? S is bigger, right? Thus, it's a bit more electronegative than oxygen, correct? Which would make that the second strongest acid. So the answer is E. Because that's the weakest acid, making it the strongest base. And this is the strongest acid, making it the weakest base. Does that make sense?
So the bigger the atom, the more acidic, right?
Yep. Because if you look at the halogens, right, you have fluorine, chlorine, bromine, and iodine. Iodine is the biggest and it is the most acidic, while fluorine is the smallest and the least acidic. That's why HF is a weak acid, even though it's a halogen.
So is oxygen bigger than sulfur, is that?
No, sulfur is bigger.
Oh, really? Why is,
Bigger atoms are more acidic
so why is number 2 the most acidic?
because it has resonance. The double bond can go up here, it could go down here, it could go here. It has resonance forms. Do you see that?
Yeah.
Okay. So 11 is the exact opposite of the one we did yesterday, right? Oops, don't look at that. Okay, amides are what? Stronger or weaker bases?
Weaker.
They are weaker bases. But they have higher or lower boiling points?
Lower.
Higher. They have more carbons on them, right? Than amides have more carbons, right? Thus, they are larger molecules, which means they take longer to boil. Make sense? Smaller things boil quicker. They have lower boiling points.
I read on mines.
Yeah, I know, it's confusing. Yeah, it's very worded really. Okay,
Wait, so amines or amides are bigger? Or does that-
amides are bigger because an amide is an R group, a carbon with a double bond, to oxygen, right? Next to a nitrogen, which could be X, which could be an H or a carbon, right? Let's assume it is a carbon. Which can be more carbon R groups, which could be more chains, right? So it could be a really big molecule. Well, all an amine is, it's an R group, right? That could be bonded to other R groups or other H's. It has one less carbon, theoretically speaking, right? 1, 2, 3, 4. 1, 2, 3. It has less carbons, less making it. Yeah, there we go. Sorry about that. Oh, I have questions. I don't like when I have questions. Oh, I have 3 questions now. Okay, what's up? Yes, that's correct. Thank you, Mackenzie. You're correct. Since amides have a double bonded oxygen, they're more acidic, right? So, yeah,
Because of resonance.
because of resonance structures. So that makes them weaker bases. Does that make sense? Yes or no?
Yeah.
Okay. Cool. Number 12, rank the following compounds by acidity. So, what is the first molecule? What functional group is that?
Aldehyde.
Oh, you're correct. Say it out loud.
Carboxylic acid.
What's the last word mean? It's an acid. Hint, hint, wink, wink. It's an acid, right? So it's probably a strong acid, right? It's probably acidic. Good. So that's going to be most likely your stronger acid right here, carboxylic acid. Let's test it though, right? We got 2 ethers right here, right? Well, resonance structures can do what? They can't do much, right? There's not. Yeah, it is. There's not as much resonance because there's nowhere to move a bond or a charge, really.
Aren't those ketones?
They are ketones, my bad. They are ketones. You're right. They are ketones. So they are acidic because they are double bonded oxygens, right? It's just they're less. They do have resonance structure though. They do bond up here, right? You could also move the bond here and bond. That's how you would do it. You would move the bond here, bond here, bond here, bond here. So you could have resonance there, right? However, what's that group right there? It's an OH with the alcohol, right? If that double bond moves right there, gives the double bond to oxygen, right? What happens to that H? It gets kicked off. I have a free floating proton. You guys love Bronsted Lowry anymore, right? So that's a free floating proton. That's an acid. So this is the strongest acid. This is the middle acid. And this guy right here is a triple bond. It's not going to do much. Triple bonds really don't react too much. Make sense? Because they're stable. It's also especially since the triple bond carbon to a carbon, there's equal pull. There's no reason the carbon to break any of its bonds. It's happy, right? So it's going to be 1, 2, 3, 12 is A.
Can you explain one more time why 1 is more acidic than 2?
Yes. So using Bronsted Lowry is the easiest way of explaining it. If that bond breaks or you form a resonance structure there, a double bond is formed here between that carbon and that oxygen, that H has to go away. Otherwise the oxygen is breaking the octet rule, right? So it will kick the hydrogen away in favor of forming a double bond with carbon because that's more stable for itself. That leads to a free radical proton, which will go react with any negative molecule it can find, which is the definition of a Bronsted Lowry acid, right? One that donates a proton, correct? There you go. That would make it an acid by Bronsted Lowry definition. That's the easiest way of looking at it. That's why that one's stronger. That makes sense? That makes sense?
Yep.
Cool. 13, how many total resonance structures? Okay. Yes, that is true, Nicole. Because it has an OH, OH groups tend to be more acidic because they want to form water. And 2 doesn't have any hydrogens to form water with. That is correct. There's another way of looking at it if you like that way too. I'm very careful with doing stuff like that because he likes to always make exceptions to those rules, Nicole. But if that works for you, that works for you. Okay. How many total resonance structures can be drawn from the following cation, including the original structure? Make sure you include the original structure. It's always important. Okay. Bond go there, right? Which would make a double bond here. Where's the positive go then? Positive would become here, correct?
Yeah.
Do you see that? Jocelyn?
Yeah.
You see why the positive moved there?
Yeah.
Okay, then I know you struggle with this concept sometimes. I'm not trying to call you out, just want to make sure you're good. Okay. Positives there. Okay. Is there anything else? Is there any other resonance structures that are possible? Yes, no, maybe so.
Yeah, you can do a lone pair from the oxygen.
That is true. You're correct. Oops, let's do that in a different color. That's where the last one comes from. Let's do bright red. No, I want to do bright red pen. Yep. The oxygen has 2 lone pairs, and since a lone pair is right next to a positive, it will form a double bond here, and that will make the oxygen positive. So how many colors do I have there? I have 3 colors, right? Plus the original structure is 4 in total. Does that make sense? There's 4 in total. Okay. Oh, I have questions. There you go. Okay. 14. Which of the following formula is based upon which one has the most structural isomers? Okay. We have this alcohol group we have this O group right here, right? Is that different than carbon and hydrogen? Could I move that around places? and do different things with it. That makes that one have the most structural isomers because I have a weird thing to play with, right? I could make ketones, I could make ethers, I could make alcohols, I could make aldehydes, right? There's a lot of things I could make with just alcohol, it's O, C, and H, correct? Yep. Okay, here I got 3 carbons and 6 hydrogens, right? Is that the normal amount I should have, right? So 3 carbons bonded to each other, right? So 1, 2, 3, that's what the normal one should look like, right? 1, 2, 3, 1, 2, 3. Hey, that's not normal, right? I should have 8 hydrogens total, correct? So it means I need to have a double bond somewhere. Having a double bond can make you have different molecules, right? That's why that one is going to be lower. Having a double bond with only 3 carbons can only go one place, right? Do you see that? It either goes there, and that's it. Because if I move the double bond the other place, it doesn't do anything, right? So it technically only has 1 structural isomer. That makes sense? Since so few carbons with 1 double bond has very few isomers. This guy right here, tons of carbons, right? Tons of hydrogens. I could make branches, I could make shapes. I could do a whole bunch of weird things with that one, right? That's the second most. So it should go 1, 3, 2. So 14 should be B.
So you don't even have to draw it out.
Nope, you don't have to. If you don't know, draw them out. But if you're gonna draw all of them out, save that, do that question first. Make sense? But there's a way of looking at it before without doing anything about it. Okay. Hello, people that just joined. Okay. 15, there is a slight positive charge on which 2 atoms, 2 carbons, or 2 atoms technically. So what's more electronegative, oxygen or carbon? So would oxygen have a positive charge? Yeah, so no. That's why that, so 1 is out. So that means that one's out and that one's out. Half the answers are gone already. Okay. What about the carbon bonded to oxygen? Are more electrons going to hang out towards oxygen or are more electrons going to hang out towards what? Oxygen, right? Because oxygen is a bully, it's more electronegative. So it's going to have the electrons are going to be this way, correct? Which makes 2, which is why 2 in both the answers is slightly positive. Now we just have to look at which one it is. Is it 4 or is it 3? Why would you say 3? They make it slightly positive or slightly negative? This guy right here is slightly positive, right? So where are the electrons going to hang out? Electrons are going to hang out towards this guy right here, right? Electrons are being pulled towards 2 because it's slightly positive, right? So between 3 and 4, where are the electrons going to hang out? Towards 3 because it's closer to a positive charge. Do you see that? Yes or no? Okay, let's try zooming in on the question. Zoom in on the molecule so you guys I can draw stuff. Let's go to the show. Okay. Yeah. So you guys told me correctly that there is a charge going that way, thus making this carbon slightly positive. That makes sense to everyone, right? Okay. The electrons in that carbon right there are circled in pink, right? Those electrons are going to kind of go towards number 2 because it's slightly positive, right? And electrons want to be towards positive things. Does that make sense? Yeah. So there's going to be a pull electrons towards 3, so those electrons can hang out and try going to that guy right there. Thus making 4 slightly positive. It's less positive than 1 and 2, but 4 is more positive because of the oxygen and inducing polarity. Does that make sense, Jocelyn, now?
Yeah.
Okay. And so the answer is C, 2 and 4. Yes, who spoke? Okay, no one spoke. How many following statements is false? So let's go through and see which ones are false. Okay. The percent of S characteristics and effective electronegativity are directly proportional to each other. True or false? Do you guys know on top of your head? No? Okay, we'll skip that one. An sp3 orbital has greater percent S characteristic than sp2.
False.
Why?
Because SP3 is 25%, SP2 is 30.
Yes, sp3 has 4 parts. 1 part of the 4 is S. sp2 has 3 parts. 1 part is S. So 1/4 to 1/3, 1/3 is bigger. Make sense? Someone's wrong. Okay. As the percentage of S characteristic increases, bond strength increases. That is true. Triple bonds are stronger than double bonds, which are stronger than single bonds. An orbital with a greater S characteristic is smaller and more compact. True. Triple bonds are smaller. The bond length are shorter, molecules are closer together, right? So the orbitals are smaller. You guys don't know. One is true.
Remember, the carbon only lost.
Who has spoken?
Hold on to the
Now it's Josh.
Hey Shane,
Yes.
can you cover the reasoning behind the fourth one again?
Yes. Oops, let's not do that. It's a carbon. So that bond length, right, allows me to have tons and tons of bonds all the way around it, right? That's what that carbon single bonded means, right? Which means those molecules want to get spread out as possible, right? That's what single bonds do. Double bonds are more bent. They have to be closer to each other, right? Triple bonds are basically the same structure. They are so close to each other, they're practically touching. If you don't believe me, and you have model kits, go make a triple bonded model. They don't want to move and they're very close to each other. The black carbons are pretty practically almost touching each other. As single bonds are further away from each other. Double bonds are closer to. Make sense, Emily?
Thank you, Shane, appreciate it.
I appreciate it too. Thank you. Okay. Joshua, do you have questions? I'm gonna take the blank answer as a no. Cool. So 1 is true as your S characteristics and electronegativity are directly proportional to each other. That guy is stable, right? It doesn't really want to react unless it can, right? However, if you threaten stabilization, it freaks the fuck out. If I put a charge on that molecule, right? For example, if I remove those electrons and now that molecule is positive, right? It is not happy because what does it have to do? It has to break its triple bond. You just made a stable structure unstable, making it very unhappy, very temperamental, right? It doesn't want to do that, correct? So not happy, correct? So its electronegativity technically goes up. A way of thinking about that, and say you want to do this. Electronegativity is the amount of electrons it wants, correct? If it is positive, it's going to want to steal electrons from other molecules. So it doesn't have to break its own triple bond, correct? Makes sense? So it's going to form a bond with something else, either another carbon or hydrogen, or gosh, forbid, a nitrogen or anything like that. It wants to be happy without breaking its triple bond. That's why 1 is true. That one's false. True, true. That's why 16 is A. That makes sense to everyone? 16 is a very, very good question to study. That way you don't have to really know anything about hybridization besides what you need to know, which is all those 3 things pretty much. Okay. Dipole. Let's talk about dipole, dipole, dipole. Yay. Okay. That molecule, does it have any dipole? Does it have any dipole? Is there any pull between those four four chlorines? There is pull, but there's equal pull from all four sides, right? So it's pulling in equal four directions equally, correct? And thus there is overall no dipole movement, right? It's equal pull. So if one has no dipole movement, is it going to be the strongest or weakest? Bing, 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 bing. Now between two answers, right? Let's look. Is there a dipole movement in this guy? Yes or no? Yes. Where is it towards? There is movement towards the chlorine. Good. There's only one, correct? Let's look at this guy. That double bond with dipole movements means it's being pulled to, you can treat it as being basically being pulled towards two different oxygen. Right? So technically there is a dipole movement, but technically you can think of it as being two dipole movements. Right? It's two bonds towards oxygen. It's basically being bonded to oxygen twice in one direction. So it has a greater dipole movement because of that double bond. That makes sense to me? If that makes no sense to you, you can think of it like this. How many electrons are in each bond? 2. How many bonds is that total? 2. So there's 4 electrons being pulled this direction. There's only 2 electrons being pulled this direction. Correct? One is pulling more electrons, this has a higher dipole movement. Correct? So 2 is going to be the biggest one. So looking back at those 2, D or F?
Even though it's double blind, it's bigger than 20. Because if we're in more electrons.
How many more electrons are being pulled towards the oxygen?
2. But say, would you like just double the electronegativity?
Yeah. Yes. That's why that is making sense. It's being pulled into 2 different oxygen. It's pulling 4 electrons of 2.
Okay.
Thus, chlorine is more electronegative, true. If that was just being a normal oxygen, 3 would be more electronegative, but that double bond does change the rules a bit. Hello, people that are joining. Where were you yesterday on Monday? Like half the amount of people, twice the amount of people actually. Okay. 18, pKa, 115 students. Hopefully you know what pKa is. So strong acids have high or low pKa? Nope. Low pKa. Ka is the strength of an acid, right? So high pKa means a strong acid. That P stands for negative log. You could think of negative log meaning the exact opposite. So pKa is the exact opposite of Ka, right? So strong acids have weak pKas, right? That makes sense? And I'm putting the largest pKa first. What's that mean? I'm putting the most acidic first or the basic first? I'm putting the most basic hydrogen first. If you get, and the people on Zoom, if you have questions, just shout them out or type them into the thing. Okay. So we looked at this molecule yesterday, right? But what makes hydrogen acidic is being near resonance structures. Okay. Hi, John. I don't know who you are, but hi. So which one is more acidic? 1, 2, or 3?
2.
Nope. Which one is near more double bonds?
4.
1 is, right? Whoa, hi, you can hear someone. Who's speaking? Oh. Okay. So 1 is more acidic. The reason being it's near 2 resonance structures and it's near an oxygen. This is the most acidic. If that's the most acidic, has the largest Ka or lowest Ka? Lowest, so it should be the last or first. Bing, 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 bing. Hey, almost all the answers are gone. See, when you're dealing with acid-base problems, pick one, right? If you like acids, I like dealing with acids way more because one set of rules, it always makes sense. And then always do the exact opposite for bases. That way you can eliminate half the problems pretty much off the bat. Make sense? Okay. Now, we have to see which one is more acidic. 2 or 3. 2 is more acidic. Good job. It's near 2 double bonds. Right? So 2 would be the second most acidic one. Right? So that would make F the answer, while 3 is being the least acidic one. Zoomies, does that make sense?
Absolutely.
That's good. Hopefully it was not sarcasm because I can't see your face.
It wasn't, Shane. You're fantastic.
Cool, cool, cool. Okay, benzene ring. What's a benzene ring? That's a benzene ring, right? Crappy drawn benzene ring, but it's a benzene ring. Here's how you also draw a benzene ring. This is kind of key to understand this problem. That's also a benzene ring, that circle there. Why do I draw a circle like that? Yeah, the benzene ring is always in a form of resonance, right? All the bonds are moving equally around the carbon at each time, correct? So let's look this up. A benzene ring has 6 pi electrons. What's that mean? Double bonds, right? Has 6 of them. True or false? True. It's always resonating, right? Each of these 6 electrons here, 1, 2, 3, 4, 5, 6, technically have a double bond at every given time, right? Thus, they always have pi electrons.
Is that because of the antibonding? Or-
You could think of the antibonding. I like to think of it because it's always in resonance form. Okay. The structure of benzene is a resonance hybrid of 2 resonance structures. That is true. You have benzene that looks like this benzene. I'll draw that one better so we can see. Right? Like that and like that. But I can also have it here, here, and here. See how they're the same structure, that just the ring, the bonds are 1 over, right? Those are technically the same structure. They're both benzene, right? Thus, benzene technically is in both structures at the same time, equally, which means the bonds are moving quickly all around. So it is a resonance hybrid of 2 resonance structures. Those are your 2 resonance structures. Benzene has alternating single and double bonds. True or false? That's false. Because it's always in resonance, there is no single bonds. It's all double bonds. Does that make sense? That's why I like using benzene like this guy right here. Because I know that it's always in everything is always with double bonds. That's why benzene is very, very stable. Okay. And what is the shape of an sp2 characteristic? Yes, what's the shape? Is what E is. The only one that is wrong is D. That's why 19 is D. If you need to know anything about benzene ring, it's those 3 things up there, those 3 check marks. So it's at 6 pi, it's at 2 hybridization forms, and it's all double bonds, and they're all trigonal planar. There we go.
What about B?
Oh, that's true too. Because they're all double bonds, they all the same length. because all carbon to carbon bonds eventually the same length. That is true. Because they're all double bonds, right? Which means there is no single bonds, plus they all are the same length. So they all share the same bonds pretty much. Okay. Oops, I see some questions. Okay. You good, Nicole?
Yeah.
Cool. So we gotta do some arrows again. Woohoo! I love arrows. They are great. You leaving? Where you going? Okay, don't tell me. I don't want to know if it's inappropriate. It's all good. So, what happened here? These two structures. What's the difference in these two structures I underlined?
The second hydrogen.
So we got a hydrogen somewhere. Where do you get the hydrogen from? Oh, hydrochloric acid. Got the hydrogen from that guy.
Oh, it's.
So chlorine is a leaving group. So the electrons break, go towards the chlorine, making this guy a positive ion. The lone pairs on the oxygen react to this, thus attacking that molecule, thus making that molecule. How many arrows have we drawn so far? 2 arrows. Okay. Next, I am going from the red molecule, I will use a different color so we can see. I'm going from this molecule to this molecule. What's the difference? A lot is different. What happened to my water? My OH2. It's gone. Well, it left, right? Oxygen's positive. Does oxygen want to be positive? No, it doesn't, right? Is it more electronegative than carbon? Thus, it can break this bond and steal the electrons. Thus, I make what? Water is over there. Water is over there. Okay. If that bond breaks, what charge is this carbon that was just right there? Positive, right? Cool. I don't like positive carbons. They want to react, right? This is really weird to think about it, but let's count our carbons. Let's use the heart stamp because it's adorable. 1, 2, 3, 4. 1, 2, 3, 4. Hey, the structure's the same structure, right? It just opened up. If you notice, those two carbons are exactly the same carbon, right? Because it has those two groups coming off of it, correct? Do you see that? So what happened with it? Why is it positive? Oh, it had to be resonance structure, right? So what happens is it breaks that bond to form a double bond here, moving the positive charge here. That opens the structure up. Two arrows plus 2 arrows gives you 4 arrows. Okay. Hey, where did this guy come from? The Cl. He came from the HCl, right? He's still in the solution. He wants to react, right? For some goddamn reason, because he does. He's going to bond to that positive charge, making this guy. So, how many arrows did I draw? 5. What's the answer? 5. That makes sense? Cool, cool. Okay, 21. How many resin structures possible, including the original structure? Okay. That guy can go there, right? And that guy can go there. And then I have my original structure, right? How many is that? 3. If that doesn't make sense, here's what's going on. If I move the bond here, or if I move the bond here, it's the same structure, right? Pretty much, it's just mirror images of each other. So pick one, pink or red. Okay, do pink then. This structure right here, if I move the bond here, or if I move the bond here, same structure. Pick one, green or purple, doesn't matter, right? But the bonds are not next to each other, right? So you can't force them to move around the circle too much. They're carbon apart, right? So they can't force hybridization upon each other. So one goes, great, or the other one goes. They don't go at the same time.
One can't, like, probably can't choose like green and then pink, and then that's like.
Well, because green, right? Because green and purple are the same, right? So we choose green, right, and pink. The reason you can't do both at the same time is because to do both at the same time, you have to be, you always gotta. I'm trying to think of an easy way of saying this. Let's look at if I move this bond here. If I do that, I'll draw the structure out real quick. Right? So here's your bond here. Here's your bond here. Correct? Okay. They originally are away from each other, right? Polar opposites of each other. Correct? If I were to move the bond, the same other bond right here, let's do, I think it was green. They're the same, they're far away from each other, right? That structure I just drew is this pretty much the exact same thing as this one. Because the bonds are far away from each other as possible. It doesn't look like it, but they are mirror images of each other. It's the same structure.
Is this the one that it's like, your 3 options are like cis, trans.
Exactly. Yep.
So why can't you move the double bond over one more?
So you're saying if they're both like this?
Yeah,
Okay. It won't work. Why? Because it just won't. The reason why is because you can't induce that negative effect. It hurts the ring. This structure right here is really weird. Doing so, you're moving all the electrons towards one side, which you'll learn a thing called ring strain later, and that affects something. And ring strain is bad. You don't want rings to have strain because then they collapse on themselves, which is a entirely different molecule, which is not what you want. But also, Jocelyn, you are correct too. Cis. If I were to move it here, I would have cis trans. If I moved it here, right, I could have trans. These are 3 options.
So like if there's another bond.
If there was another bond, you could, yes.
3.
Yes.
Kind of confused on this trans thing.
You know what cis and trans means? Okay. To have cis and trans, you have to have a double bond. So let's look at the easiest example. Those chlorine molecules I just drew are in the same side. Yes or no? They're both going up, correct? That is cis. Cis means same, right? We use that word in chemistry a lot. We use that word in biology a lot. It's a scientific word. Cis just means same, right? So as a cis molecule, because two large molecules are pointing both up, theoretically speaking. Does that make sense? If I were to erase that and flip that around and put one down here and one up here, see how they're opposite to each other, right? That's trans. One's going up, one's going down. Does that make sense? Okay. With the molecule in the box, Both carbs are in the same direction. Both carbs are in the same direction. Right? If I were to move the double bond, one carbon will be going down, one carbon will be going up. Right? That is trans. So there we go. Okay, moving on. 23. Okay. Hey, oh, sorry, not 22, not 20, 22. Hey, it's asking directly for what? Bronsted Lowry. Use your Chem 115 brain. What's an acid?
They still electrons.
Bronsted Lowry donates what? Protons or electrons? No, Bronsted Lowry does protons. Have to know the difference between two acids. The one you guys know from Chem 115 is Bronsted Lowry. That's the movement of hydrogens, right? Lewis is the movement of electrons. We mostly use Lewis, but we can use Bronsted Lowry sometimes because it's easier to see. So that guy right there, correct, has how many electrons? Not electrons, sorry, protons. It's got what? How many protons?
2,
Protons.
1,
Protons.
3.
2. I was talking about Jocelyn. Jocelyn's the one that messed up. That's why she kept saying weird numbers. It has 2. How many does this one have over here? 3. Correct? No, I'm talking about protons. Protons are H's. How many H's does it have? How about that? How many H's does it have? Right? Okay. So does it get an H? Does it get an H? Yes or no?
Yes.
It gets an H, right? That makes this guy the acid. Correct? Okay. Hey, what do these two arrows mean? So that means the other side could also have an acid as well, right? Which one gives up which one gives up its acid? Which one gives its hydrogen on 3, 4? The one that just got the hydrogen can give it up to make this guy. Correct? Make sense? If that doesn't make sense, let's go it this way. This is my acid. This is my base. This is my base. The acid becomes the base. The base becomes the acid. Where are my two acids? 1 and 4. Because there's an equilibrium here, I need to dictate both acids are important. If it's a single arrow, I only care about reactants. I don't care about products. Zoomies, how we doing? Cool. Welcome to OChem 2 in a nutshell is this question right here. If you do this question, you'll be okay for OChem 2. This is right here, it's called a mechanism or called a scheme. So what happens is if I have, what's that structure right there?
That's the ketone.
Okay, it's a ketone. I have a ketone and I react it with a carbon, an alkene group, I think. Yeah, it's still one. It's always hard for me to say it with my dyslexia. With a lithium there, right? Lithium is a what metal? It's an earth metal, right? Do I make structures of earth metals at all? No, I use gases, right? So that lithium is just there as a placeholder. It technically doesn't want to exist. It goes away, pretty much, right? So I basically have two carbons right there. Those 2 carbons are going to get added to something. They get added to my ketone molecule. Do you see that? Here's where they came from. They get added right there. And then I made what? What did my ketone become? That is true for all ketones that react with lithium. You add whatever was attached to it, correct? And the ketone becomes a alcohol group. Does that make sense? Does not make sense? Okay. This is what I start off with. Okay, let's do some work. This guy right here leaves, right? Okay. What's that make this molecule right here? If lithium is a metal, which is positive, that guy is negative, right? If I move my bond up here, what's it make oxygen? Do negatives react with negatives? But that makes that carbon right here positive. This negative will bond to that positive, forming this structure right here. That guy got added onto that bond right there, correct? Great. I have a negative oxygen. It's going to steal one of the hydrogens from the water to form that structure. Does that make sense now? Yes or no?
Yeah.
Would be so lost myself.
Yeah.
Okay. Basically, if you have a ketone, wherever the carbon bond to the carbon bond to the oxygen is going to get added wherever it was bonded to the lithium. And then the ketone then becomes an alcohol group. That's pretty much what this whole mechanism is saying. Here's my target compound. How do I get that with a reaction? Let's look. So my alcohol group's right here, right? So that means I have to have a carbon that has a B double bond right there, correct? Okay. What's right below it? A methyl group, right? So which one of these guys has a double bonded oxygen with the thing going down? Does A have see, A is missing that little guy right here, that green piece right here, right? That won't work. B is missing the guy that goes down, doesn't work. D doesn't work. C works because it has that piece right there, right? Let's look at this quick. Nope, I don't want to draw lines. 1, 2, 3. 1, 2, 3. Hey, I'm not going to add any carbons on that side, right? But I have 1, 2 carbons right there. 1, 2 carbons right there. So that's where I get those 2 extra carbons from, is from the lithium. So C is the correct mechanism to get a target compound. Zoomies, you got it?
Yes.
Cool. Thank you, Kate, for responding. Okay. Hey, this is a lab-like question. You guys should do this class. You should do this because you guys had lab. I have molecule 1, 2, 3. Where would they end up if I'm looking for molecule 2 and 3? So 1, polar or non-polar?
It's polar.
2,
It's polar.
2 is non-polar.
Can you go back
A
a little bit?
little bit, but not too much. 3,
Yes.
polar or non-polar?
Oh, it's polar.
It should be polar, has an issue though. What's the issue with it?
Two O's.
Has a huge carbon chain. It's a big molecule, right? Looks just like a fat molecule, right? Those are it's slightly polar. Not very polar, slightly polar.
So
Okay.
are they polar?
Huh?
Are they polar?
This guy is polar,
Oh, right.
right? Slightly polar. This guy is non-polar whatsoever. This guy is slightly polar as well. So I wash them with HCl and ether, right? They all come through because I wash them with both, right? HCl is a polar molecule, right? Ether is non-polar or polar.
Non-polar.
So everything comes on through, correct? Okay, all molecules are here now. If I wash with water, what comes out? 1, 2, or 3? So is water very polar or slightly polar?
One.
It's polar.
Water is very polar, right? Is there any extremely polar molecules between 1, 2, and 3?
One.
1, yes, 1 will go up here, but do I care about 1? No, so all this guy goes away
I don't care about one.
because I'm looking for 2 and 3 in the answer.
Oh, okay.
So both 2 and 3 head downwards, right? And then I wash them with NaOH and ether again. Do they both make it through? Yes, they both make it through. Now I'm here. Okay. If I wash 2 with E, it's gonna go down here, right? Correct? Because 2 is nonpolar. Okay. SP is gonna go this way, right? And then it's going to end up. Let me just check something real quick. I believe it ends up in D. Yes, it does. It only goes up once because it's the only thing it can do. And then it goes down here. That is the layout for that molecule.
What does the NaOH have anything to do with it?
So here's why I want to do that real quickly, but here's what happens. When you react something like this, you do wash it through, right? But the hydrochloric acid is going to react with stuff, correct? If I add an H to this guy, what happens?
You get water.
I get water, correct? That guy goes away, right? So now I just have what? I just have a double bonded oxygen with those right there, correct? That's why it goes on the ether side, because it lost the OH. It lost some of its acid, correct? Doesn't really affect that guy at all. That's why you also wash with ether. Okay. Hydrochloric acid can add an H to this guy, making this guy kind of positive, which is why he goes up when you wash him with water. Right? The OH brings back the OH on option 3, which is why it reacts with water. Correct? You add the H again, the OH goes away, that's why it reacts with ether. It's basically what's going on. Okay. Zooming, does that make sense?
Kind of.
Okay. The new Zoomies that came in, do not be afraid to speak. Ask questions if you have questions. Yeah, this one is not as easy, but some of the questions are super easy. That one, some of them, it's like 2 so far have been really hard, but the rest of them have been okay. Version B, yeah. Version A was a little harder, I think, than version B. Yeah, it's harder ones. Okay. An atom with a negative charge on it. Which parameter matters the most? I don't know who that is. Does anyone know who he is? Yes, no. Anyone know who Easy is? Speak up now before I kick him. If I kick him, he can't come back. And if it's a student with an extra laptop or something, that's fine. But I don't want him to do anything stupid on my call. Okay, wait, where'd he go? He went away, okay. Well, just fine, but people do Zoom bombs, where they'll just like find a bunch of algorithms, and they'll just join random Zoom calls. And I don't need someone to put porn on the computer. That's what they do in Zoom some places.
Has that happened to you before?
Me, no, but it's happened at my mom's school, who's a high school teacher,
Oh, that's funny.
which is actually illegal because you're showing underage people sexual material, which the person who was a student who did it got in big trouble because they could have gotten majorly sued, become a sex criminal. See, by 181 class. Kenzie said it happened in her class. It's Zoom bombing's a thing. It's so stupid. Okay, atoms with a negative charge on it. What is the biggest thing about it? 25 is what? What matters most for molecules? the type of molecule matters the most, right? Is it fluorine? Is it chlorine? Is it bromine? Is it iodine? The shape, electronegativity, right? The size, that matters way more than resonance. Resonance matters second, which then up next is hybridization. One exam done. Okay. 25 was A. And then 24 was F. It ended up as ether and ether. Who's saying stuff in my Zoom call? Okay. You leaving, Athena? Easy Money left. I don't know why Easy Money left. I don't know if they got called out or someone kicked them. Because I have some co-hosts in here who do that better.
Hey, Shane.
Yeah.
It's Emily, by the way.
I
I'm
figured.
gonna leave right now, but can you just text me when you're done and ready to do micro?
Yeah,
Thank you so much.
Thank you, Shane.
of course.
You're on micro too after this?
Yeah.
Yes.
Same.
I haven't, not three.
You have your-
70.
Mine would be complete opposite. I had genetics at 7, but 3.
I'm not doing that. Don't do that.
Shane, I might head out as well.
Okay, see ya.
Appreciate it.
I will post this later. Okay, see ya. Hey, number 1, count carbons, count hydrogens. We've done this before, right?
Right.
Hint, hint, wink, wink, it's popped up in 3 practice exams. That question will be on the test. I have a little less time with exam 3, so I might make more mistakes, whatever. I might. That.
Wait,
What?
okay, this is Kayla.
Bye.
For one, can you do the EU equation as well, or just counting?
You can do the EU if you want to, but it's gonna take more time than you want, but you could.
Okay, thank you.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. Your EU is 10. There we go. I did the equation by counting. But yeah, EU equation could work too. But I like counting all the carbons, and hydrogens, and nitrogens. That makes more sense than doing math because math sucks. Okay. That's an amide, right? So let's look. Double bonded oxygen next to a carbon. Bada bing, bada boom, 2 hydrogens. 1, 2, 3, 4, 5. There we go. That's 1. Then we go here, and then we do this, and then we move it over just 1. And then we do nitrogen, and then we do a carbon, hydrogen. Bada bing, bada bing, bada bing, bada bing, bada bing, bada bing. There we go. There's 2. And then we have there's 3. So we could do this. We could take the bond, double bond it to there, put the nitrogen here, and then make 2 carbons come off of it, right? 1 hydrogen here. That's one possibility. There's 3. Same thing, right? But this time I need 1 carbon up here and 1 hydrogen down here. And hey, there's 4 total. I agree. Which of the following correctly matches the types and names of functional groups? Hey, aldehydes only appear on primary, secondary, or tertiary carbons. What do you guys think? Only appear on primary carbons because they have to have a double bond and a hydrogen, right? The double bonded oxygen and hydrogen, how many bonds is that total? 3, which means only leaves up to 1 bond to a carbon, right? So aldehydes can only take place in primary or outer carbons at the end. That oxygen right there is where? Is it in the middle or at the end? Is that an aldehyde? No, it's a
Ketone.
ROR. That's a ester, ether. Esters are different. Okay. Is that a carbon bonded to nitrogen with nothing attached to nitrogen? Hey, that's a triple bond of nitrogen, right? Is that a nitro? Yes, so that's a check mark. So which one has 2 correctly? That one's wrong. That one's cool. That one's cool. That one's wrong. And that one's wrong. So between C and D now. Okay. Carboxylic acid is what? Do I have 2 O's and an H right there? I have 2 O's and an H right here. Good. Check. What's going on here is it looks like this. It's not an ether, that's a ester. That's different. The answer is 2 and 3. It is kind of tricky, but even if you knew that, just knowing this one and this one, you get the right answer. Okay. Hey, look, it's the exact same question. Functional groups heavily tested on this exam. So if you don't know your functional groups, know them now. Make flashcards immediately before you go to bed tonight. Make sure you understand them all. Okay. Hey, 1 second. What's the Y in alkyne mean? Is that a triple bond? That is true. It is, huh? Okay. So 1's correct. Bada bing, bada bing, bada boom. So now I'm only going to check what? 2 and 4. I don't even have to check 3 anymore. You like that? That's nice. Cool. What's an amide? Amide is when you have this. It's basically a double bonded to a nitrogen when it's double bonded to a carbon double bonded to an oxygen, right? That's an amide. Is there an oxygen too? Then it can't be an amide. So what's the answer then? You guys out of it? It's only 9 o'clock. Okay. Okay, this one you just count, you're just finding the functional groups on here. So let's look at A quick. Let's look at A first. Do I have amines? Amine are just nitrogens. Okay, do I have an amide? Do I have an aromatic? Do I have an ester? I do. I have a that. No, I don't. So A is wrong. Oh, ester, don't have that either. Hey, look, ester, don't have that either. Oh, I have an ether. So that's one left over. Well, this was a real test that someone took. The fact that this one's so much easier, I would feel bad because I would be pissed if I didn't have C.
That's what I was saying, like, B was so hard.
Well, only 2 parts of B were hard. I think A was harder in general, had more harder questions. It had more hard questions at the end, that's why it simply had more harder questions. Okay. Amoxicillin, also a thing that fights things like the bad sex diseases. Let's see. What do I have? Do I have an amide? Yes, I do. Do I have amines? Technically, my bad. This is the That would be right there would be that would be the amide, and this right here would be the amine. Cool. Alcohol. Nope. It's a phenol. Because it's double bonded, because it's double bonded to a benzene ring, very, very special. That is a special molecule because it does special things.
What is it that's so much? It's the.
Because the OH is there, that's not an alcohol, it's called a phenol. So A is wrong.
Oh,
C is wrong. What's the difference between B and D? Okay. Do I have an ester?
no.
No. D.
So a phenol it's always totally chocolate.
Yep.
Okay.
What's the sulfide?
What's this? It's a sulfur.
Thiol,
Is
right?
that one of the ones we're supposed to know, sulfide?
Yeah, it's just a sulfur in a molecule.
So what's a thiol?
Thiol.
Isn't that something one?
Thiol is a sulfur bond to an oxygen.
Oh, an oxygen.
Yes. Zoomies, you're still here. Okay, I lost some of you, but it's all good. Okay. Strongest acidity. Two, three, one. What do you think? Is that your final choice? Is that your final choice? No. Strongest acid first. The strongest acid is 1. It is a nitrogen chill bonded to a carbon, right?
So it's
That positive charge right there, yes, you can do, if you want to do it's SP, which is the most acidic, right? So hybridization helps you with that one. Otherwise, you can look at, does that positive influence that triple bond? That positive threatens it, right?
Oh, yeah.
It threatens the triple bond. Is that molecule happy?
No.
It'll kick that hydrogen to the curb faster than my X left me. There we go.
It was a good thing, huh?
So that's why 1 is the strongest acid first. Okay, what's stronger, 2 or 3? Which one has resonance structure?
3 or.
So the answer is B, 1, 3, 2.
That's basically what I said.
Yes, that's what, but that doesn't help. Zoomies, you understand this? Anna, all you guys, more names that I want to say out loud. You good?
Yeah.
Cool. I know you guys probably haven't been to my Zooms before. You guys can talk as much as you want. I'm here to help you guys ask your questions. If you are my Zooms before, and I don't know who you are, so I can't see your face. Okay, for the molecule, how many structural isomers exist? I'm not going to draw them all. A lot exist. Draw them all out if you want to. The answer is 8, but you're close. The reason why it's 8 is because it's one bromine. That bromine can pop up on tons of different carbons, right? Because they can exist on primary, secondary, and tertiary carbons, correct? Thus, because of that functional group, more isomers can exist. That make sense?
Yes.
Yeah, or if you would have to draw it, yeah. That's why I would do that one first to get that on your test. Yeah. For the acid-base reaction, which is removed by sodium hydroxide? Hint, wink, wink. What's more acidic, the outsides or the insides? Outsides. When you guys are old enough and you're not going to GCU, you go to a bar, you try to approach either guys or girls, depending on your preference, right? My experience with a girl, so I'll go over this story. It's harder to pick up on the chick in the center of a gaggle of girls because she's protected by the flanks, right? So you have to talk to the outside ones first. Does that make sense? Now you guys laugh. It's gonna be in your mind forever. A gaggle of girls. Well, what do you call a group of girls? A gaggle of girls. You call a group of guys just dumbasses. That's what they are, because a bunch of guys together, it never ends well. Someone's gonna end up being hurt. So C, B, D are wrong. C, B, D, E. Huh? You guys can. I am an instructor that's being recorded right now. I am upholding all of GCU's values. I'm holding up all GCU's values. Okay, so it means we either do with A or F, correct? Is it? You would think so. It's F. Because it's NaOH. So that bond moves there, which moves that bond there, which moves that bond there, which kicks off a hydrogen. So the answer is F. If those bonds in the middle weren't there, then it would be A. But since those bonds are there, it can do a resonance structure and push the negative charge or push the positive charge all the way to the last carbon, kicking off that hydrogen right there, making it an acidic H. Does that make sense?
Why can't it kick off the H right there?
It can, it could, but more pulls on the other one, right? Because it could move the bond, it could technically, that is an acidic H, right?
Yeah.
But this one's just more acidic because of these bonds placements, because that one has more resonance structures going in this direction than the other direction. That's why F is the answer. Okay. 10. How many resonance structures do we have? We have one going that way, right? Which makes the positive on that direction, right? We have lone pairs in the oxygen, which form a bond going that direction, correct? Let's do a different color though. Let's do red. Boom, 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 boom. Bonds go here, which puts the positive charge on that oxygen right there, right? Let's switch to pink, which moves that guy right here, which puts the bond here, which puts the positive right there, correct? Which then moves the double bond from here to here, which puts the positive charge right there. The answer is 5. There's one more, it moves it backwards, but I don't have space to draw it. The answer is 5. Including itself. So there you go. I think I messed up one of the moving of positive charges, but the answer is 5. 4 including itself. So rank the following by dipole movements. So which has a greater dipole movement? Triple bond, double bonds, or single bonds? So which one has a triple bond? So that's the highest dipole movement. Okay. 11's A. See, test C is very easy. I was just scrolling through it real quickly. I thought it's hard yesterday, but it's actually the easiest one, which is annoying. Okay. Zoomies, how are we understanding all this? Okay, no response. Hopefully you're all good. If not, I'll have some screaming a little bit. Okay. Which one is the highest boiling point? You could look at the pKa chart, but which one has more? Okay, hopefully not going to kick us out yet. It's not 10 o'clock yet.
Oh, is it next to blood change or the?
Yes, cool. It is. So that being said, right? One is going to have the highest boiling point. Why? Because it has larger carbon chains. It's got more branching. Branching affects something, right? So think of a person. If I put a whole person into a pot of boiling water, take longer to boil. What if I cut someone's arms off? They boil faster, right? Because the body has less stuff and the arms boil faster, right?
Yeah.
So branching does affect boiling point. More branches you have, more surface area, longer it takes, higher boiling point. So A is first.
Bigger molecules.
Bigger molecules, more branching, more carbons.
Subject molecule.
Yes. What weighs more? Actually, technically, what weighs more? 2 or 3? 3 weighs more. Thus it boils, it takes longer to boil. It's heavier.
Could you also, I know it's not a branch, but like the connection between the hydrogen and the nitrogen.
That you could count that, yes, if you wanted to, but I would do more with weight. Because it's pretty much the exact same structure, right? But it weighs a bit more
Why does it weigh more just that?
because the hydrogen's there.
So then you could use so if it's like the same structure, just look at the weight.
Also, nitrogen to hydrogen, that's not carbon, that's oxygen. What are hydrogen bonds again? What molecules? Hydrogen bonds.
Isn't it like carbon? Oh wait, or is it the one where it's like Br and then like?
No. Examples. Yes, so it's also because of hydrogen bonding too. I'd actually say hydrogen bonding over weight. So I just look at the weight of both of them. That one is not going to overcome it. It's hydrogen bonding. My bad. Hydrogen bonding between and 3 is better. So when hydrogen is bonded to nitrogen, oxygen, or nitrogen, oxygen. Cool. 13. Don't ask a question. Cool. Okay, 13 is what? What is the correct association of conjugate acid conjugate bases? Number 1 has a negative charge. Except the what? The nucleophile, which makes that the, which makes this guy the acid, which makes this guy the conjugate base. Which one's that? Acid, base, conjugate acid, conjugate base. C. Which one shows the correct flow of electrons? A. What's wrong with A?
It's not, it's positive going to like.
Arrow showing moving electrons. E has a positive. It can't move electrons, right?
So it's the same thing with C.
Yep. Same thing with C. Okay. What's wrong with B? Is there anything wrong with B? I don't see anything wrong with B. What's wrong with D? There's a hydrogen here, right? Why did the hydrogen get kicked off? It wouldn't get kicked off. D's wrong, right? Because if you're gonna kick this hydrogen off, you have to show the arrow for it. It doesn't show the arrow for it, right? What's wrong with E? Kind of the same thing. It's not showing. It's showing the arrow from the bond going to it, right? It's not breaking the electrons and then doing that too. Also, if H were to leave, would it be positive or negative?
Positive.
Can positive bond with positive? No, that's why E is wrong too. The answer is B.
So also because the arrow was going directly towards the E and it wasn't.
Yep. How many sp2 hybridizations do I have? think I have two? You see two? Huh, SP2, so that's when it's bonded to two different things. Sorry, three different things, sorry, three things. 1, 2, 3, 4. Right, there's one more. Oh, here. And the oxygen up there does count too. Because it technically has these electrons are technically groups, so it has 3 groups. Has a carbon and 2 lone pairs, which don't really count. I don't really can't count them as bonding, but they are groups that could bond, so they do count as one thing. The answer is 5. Okay. Anyone have any questions? Speak now. Oh God, a set of pi molecules are generated by various linear combinations of p orbitals. Which of the following is the highest energy? C is the highest energy. Because you got up and down, up and down, up and down, up and down, right? It's
A the lowest then?
A is the lowest. B would be the second lowest, D would be the second highest, C is the highest energy.
Hey Shane, I'm kind of confused about 15. Why was the nitrogen sp2?
1, 2, 3. Oh, you're right, it's not. You're correct. 1, 2, 3, 4. There's 5. I know that. I just don't forget I forgot how I got 5. Oh wait, 15? Yeah, 15's E. 15's E, yeah. Itself 1, 2, 3, 4. I'm just missing the 5th one. You could be right. It could be an answer in the wrong with the key. As I said, I didn't really look at 3 too much. I just have the answers written down.
Should be sp3, because there's 2 lone pairs and 2 bonds.
Yep, that's 4 things total.
So then why is the first oxygen?
The first one? 1, 2, 3. Yeah. So I'm only seeing 4. So the answer key says 5, but I'm only seeing 4. I don't know what the last one is. It's 1, 2, 3, there, and there. I'm seeing 4. I'm not seeing 5. You're correct. I should have the nitrogen because I thought I saw one there, but you're right. That lone pair there does fuck it up. Oh God, I'm getting some messages on Zoom. Yes, there you go. Thank you, Mackenzie. You could have spoken up, but you didn't. C is the highest energy, A is the lowest energy, B is second lowest, D is second highest. Okay. 17. Seventeen is, what's going on with 17? How many curved arrows? Oh God, I hate these ones. These ones take forever.
Yeah.
Okay. If you notice, you can't do that. You can't just skip directly to the end product, unfortunately, right? Don't do that. So what's the difference between this molecule and this molecule?
Double bond, NO, and hydrogen.
So I have to lose my hydrogen, right? So that guy goes here, right? That goes here, it breaks the hydrogen, and that goes there. And now I have that structure, correct? Okay, I will make the molecule bigger. 1 second.
Oh, the one was up.
Well, I'm gonna draw it again because, oops, no, wrong way. This bond goes down. It will go up, you're correct. My bad. This bond goes up, right? this guy will go here, right? Reason because this guy became slightly positive. I need a slightly negative thing right next to it. It's gonna form a double bond here. Correct? With those lone pairs I broke off from the hydrogen. Correct? You can see it technically. Will go like this. And then these lone pairs will attach that. So far 3 arrows. And then this bond will move up to here.
So you move up to the O first. Yeah.
Yep. Make that double bond, which is right there. That makes this guy right here slightly positive. Electrons leave the oxygen and they attach right here. Yeah. So arrows 17, the answer is D, 7. Okay. Okay. How many curved arrows? We got a lot going on here. Okay. What's going on? Well, we got to break a molecule apart. This is awful. Okay. First things first, this bond goes up here, right? Making the oxygen negative. Making that carbon right there positive, making that guy attach. That's how I get the second structure. From here, chlorine leaves, making this guy right here slightly positive, right? Because of that, I break this bond, right? Move it towards this guy, make a double bond, move that one down here and make this structure. The answer is 5.
You maybe do the middle one again.
Yes, I can make it bigger too.
Keep your color, just all look the same.
Okay, that's why I want to make it bigger. Let's make it bigger. Okay, let's see different colors. Let's do red. Okay, leaving group leaves, right? Okay, since that occurs, this carbon right here becomes positive, correct? It's going to break this bond to make that bond double bond, which breaks the ring up, correct? Okay. We then take that double bond, that negative charge on the oxygen, move it down, make that right there occur, and that's how we get structure 3. So those 3 plus the original 2 we had to begin with gives you a total of 5. So there's 5 arrows. If you notice, he likes closing rings or breaking rings apart. So make sure you understand how to do that. Counting carbons is the easiest way. 19, write the compounds by basicity, strongest base first. Is the triple bond happy?
Yeah.
Yeah, right? It won't break the triple bond, correct?
Yeah.
Thus, it's stable. Does that make sense? So is that a strong base? Oop, wait a sec, 1 second. All right, misread the question. So it should be happy, right? But there's that negative charge there. So it's gonna form a bond, right? So technically, it being negative, it is a base. I would do the strongest base, my bad.
So that'd just be going up.
Oh, never mind. Let's look at it this way. Let's look at hybridization because they're all, if it's 1, 2, 3. Let's look at that way instead. Because they're all negative charges, right? Let's look at hybridization. What's hybridization of this guy right here? sp3, sp2, sp. So the higher S characteristic, more acidic you are. So we're actually, if it's actually opposite sp, it's gonna be 1, 2, 3. It is. The reason why that base is technically more acidic is because it does have negative charge. We'll want to get rid of it pretty frequently. So it's not as much of a threat as a positive. but it's still not happy.
But if it was asking for an acid, then it would go 3 to 1, right?
Yes. Indicate a carbon atom. Okay. That carbon right there, what is it? Does it have? So can I break that bond up? Can that bond go to this carbon right here, theoretically speaking? So it can have, it could have a lone pair, in theory, right? Which would make it electrophile or nucleophile? A nucleophile, because it has a lone pair, it's negatively charged, right? Negatively charged are neutrophiles. Is it a nucleophile because it's electron rich or electron poor? Electron rich. You only become a nucleophile if you're electron rich. A poor electron poor nucleophile is an oxymoron. It really can't occur. Yeah. That makes sense? You can't have that.
So you just have to know that there's like possibility for there being lone pairs.
Because resonance structure. Resonance structure sucks because you have to know that it technically is there at all times.
Problem is it could just be a hydrogen.
It could be, but yeah. 21, resonance structures.
Which one is this?
So we have that bond right there, right? That negative charge, correct? So that has to become a lone, that has to become a double bond somewhere, correct? I have two choices. I had the red choice, which I put it here, which then breaks this bond and puts it onto that carbon. Or I have the blue choice, which moves it here, breaks that and puts it on the nitrogen. Those are the only two options. What two options are those ones?
Oh.
Yeah, 4, 3. 21 is C. Or 3 and 4, whatever one makes sense. Okay. 22. NaOH reacts as a Bronsted-Lowry base with that guy. Which compound formed with reacts as a Bronsted-Lowry base? So Bronsted-Lowry, am I moving a proton or electron? Okay. If I remove a proton from something, correct? What do I make? I lose a hydrogen, right? Which means I gain electrons. If I gain electrons, I can make a double bond, correct? Which one is a double bond? B is the answer. That's why. B is the answer. Because I form a double bond. D and E are examples of Lewis structures because they form together, right? That's a no-no. Same thing with A. Oh, also same thing with C. Hey, notice they all are Lewis structures because they all get added. Lewis structures, you add the two components together. They form together to become happy. Bronsted-Lowry, you just add the height, you take away a hydrogen, and then that's it. They don't come together. You still have two different products. Okay. Where is the hydrogen going to go? Towards the nitrogen or towards the oxygen? Okay. But why? Why would it go towards the oxygen? There we go. So which makes an alcohol group? A and B, right? See A and B. Okay, let's see which one's true.
No, maybe.
The answer is B. Good job. Why'd you say B?
That's on the double bond, making farther, you have to move that bond. You see, okay, so you see on this one, how the double bond is like on this side.
Yeah.
And up there, it's over here, so I figured if it's gonna go towards it, it has to move it.
Exactly.
Where's the one grab, actually?
It could do that. That is a possibility. But it's more likely to attach the oxygen because it's a higher chance of it occurring. But if you can't see what's going on, for A to be the right, for B to be the right answer, which it is, right? It's gonna move this double bond here, making this slightly positive, doing here to here, making that slightly negative. Attaching that to there. Yeah. Move the arrows aren't moving correctly. 24. Pyrimine is provided by an acid. Which the 4 labeled carbons is the positive charge least distributed for?
Thanks, Shane.
See ya.
Have a good one.
Which of the 4 labeled atoms is positive charge least distributed on? 4? Can I put a negative charge on that guy right there? I can't break that bond, put a negative charge there?
Oh, yeah.
Can I break that bond, put a negative charge there? Right, I also could do the same thing with 1, correct? The only one I can't put a negative charge on is 3. Because there's no, like, I technically could do that, right? But doing so would indicate, it would move the whole thing around. It would not work as well.
Oh, because there isn't one to the, oh.
Because there's no double bond.
Yep,
Yeah, okay. So this can be 2 double bonds adjacent to each other.
yep.
Nice.
Okay. I mean, I am going to quickly through these questions because in about 10 minutes, they're going to kick me out and the computer shut down. So I want to be able to upload this to YouTube tonight. So let me just briefly go through the last one. Okay, a chemistry student wants to separate the molecule, separate a mixture of benzoic acid, nepylene, and N-butylene. First, the student must add an aqueous hydrochloric group to the mixture. The student takes the aqueous layer and adds NaOH until the basic and extracts the aqueous layer with ether to give solution A. Second, adding blah, 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 blah. So this is the exact same thing you already played with without the flow chart. This is more of a lab question. But the answer is going to be E, right? So basically it's asking is if you add a hydrogen, right, and extract with an ether layer. So A, the reason why you're going to extract an after you add an H to all those molecules, right? You could basically make this molecule, right? You add H there, that molecule can leave the group, right? Theoretically speaking, correct? Thus being kind of happy. So it can be washed out with ether. That's why that one's there. Solution B is nepylene because after watching with NaOH, it goes back to being kind of technically stable, right? Which is here. Lastly, it's that guy because you wash it out like after reacting multiple times. So yeah. There's your answers. There's pH really. There you go. But there's all your questions. Of course. Zoomies, any questions before I close the thing up? Anna, Mackenzie, Arsh, me, Nicole. Okay. You want help with micro too?
I already did micro.
Oh, you already did micro?
I took micro.
Okay, I'm gonna close the Zoom. Thank you.
I do genetics now. I took micro my first semester sophomore year.
So you can take, or you have